All right, today we're diving into something pretty cool. We're looking at how scientists are literally building a better pollutant zapper, cooking up custom materials, atom by atom, to clean the very air we breathe.
So just imagine for a second, what if you had a special powder, and this powder was so powerful that it could just break down harmful pollutants with a tiny little zap of energy? Well, that's not science fiction. It's actually the goal of some really clever material science.
Okay, so the hero of our story is this material called titanium dioxide, or titania for short. And you can think of it as a real workhorse. It's cheap, it's stable, and it's a fantastic photocatalyst. Now that's just a fancy way of saying it uses light to kickstart chemical reactions that, well, they obliterate pollutants. Pretty great, right?
But you know, every hero has a weakness, an Achilles heel, and titania's big problem is that it needs a really powerful blast of high-energy UV light to get going. And using those strong UV lamps, well, it's expensive and it just eats up energy. That really limits how we can use this otherwise amazing material out in the real world.
So, how do you fix a hero's fatal flaw? Well, the scientists behind this research decided to do what any good chef would do. They decided to tweak the recipe. They started wondering if maybe, just maybe, adding a little something extra could unlock titania's full power.
The secret to their new recipe is a process called doping. Now, it might sound a little weird, but it's a really fundamental idea in material science. All it means is that you intentionally introduce a tiny amount of an impurity, in this case, another metal, into a pure substance. Why? To give it brand new and hopefully improved abilities.
And that right there brings us to the biggest question of this whole experiment. Could doping titania, adding just that tiny bit of another metal, allow it to do its pollution zapping job using a much, much lower energy light source? Could that make the whole process cheaper and way more practical?
So, the mission was set. They were going to dope titania with a very specific transition metal, vanadium. The hope, the goal, was that the vanadium would act like a tiny antenna, helping the titania absorb lower energy light and basically turbocharge its performance.
Now, you have to understand, making these custom nanoparticles, it is not like baking a cake in your kitchen. We're talking about a furnace heated to a blistering 1,000 degrees Celsius. And as we're about to see, how you add the ingredients to this crazy hot furnace turns out to be incredibly important.
The whole process is kind of like creating microscopic dust from thin air. First, a chemical vapor with titanium in it gets fed into the furnace. The insane heat breaks it down into individual titanium molecules. Then, those molecules start bumping into each other and sticking together. That's a process called sintering, and they build up into these tiny nanoparticles. The researchers tried two different ways of getting the ingredients into the oven, so to speak. The first one, the bubbler, is kind of gentle. It heats up a liquid until it becomes a gas, and then that gas flows into the furnace. The second one, the atomizer, is much more direct. It's basically like a fancy spray can that shoots a fine mist of the materials straight into the heat. And this is where things get really, really interesting. Because the scientists discovered that the method they used, the way they made the particles, had a massive impact on the final product. It turns out the how was every bit as critical as the what.
So first, let's look at our starting point, our control group. When they made just plain old titania using that gentler bubbler method, they got a very specific kind of particle structure. The bubbler method made these teensy tiny primary particles, only about 10 nanometers wide. And these little guys would link up together into these long, chain-like structures. The bonds between them were really strong, almost like they had partially melted and fused together. But then, when they switched to the atomizer method and sprayed in that vanadium dopant, everything changed. This one simple change to the recipe completely transformed the material they ended up with.
With this new method, the primary particles were suddenly twice as big, about 20 nanometers, and they were much, much more spherical. It turns out that adding the vanadium this way actually sped up that sintering process, encouraging the particles to merge more completely into these rounder, more uniform shapes.
I mean, just look at the difference. The particle size doubled. The shape went from long chains to nice round spheres. and the whole process shifted from just a partial fusing to an enhanced, more complete fusion. And all of that was just because of how they added the vanadium.
Okay, so they've created a totally new material with a completely different structure. That's cool science for sure. But the real ultimate question is still on the table. Does it actually work any better? To find out, they had to put it to the test against a common air pollutant called toluene.
And here is the absolute key to the whole thing. They didn't cheat and use a big, powerful UV lamp. No, they used a very low-energy system, a combination of a corona discharge and soft X-rays. This was the test that would prove if their new recipe actually solved the original energy problem.
And oh man, the results, they really do speak for themselves. With just the low-energy system alone, it broke down about 35% of the pollutant. Okay, add in the original, regular titania, and that number bumps up to 53%. Better, but the new vanadium-doped titania, a whopping 69% degradation. That is a huge improvement.
69%. That's the number. That number proves the whole concept. The new recipe, made with that atomizer method, created a material that was just significantly better at cleaning the air. And, this is the most important part, it did it without needing a crazy expensive, high-energy UV lamp. Mission accomplished.
Now, this might seem like one small, very specific lab experiment, but the implications here are actually huge. This is about more than just one new material. It's about a whole new way of thinking about how we create solutions to big problems.
So, what are the big takeaways here? First, the way you make a nanomaterial is just as important as what it's made of. Second, that doping process is an incredibly powerful tool for customizing a material to do a specific job. Third, we can find smarter, lower energy ways to turn these materials on. And finally, all of this is a really important step towards building better, more efficient technologies to keep our air clean.
This quote really just captures the whole spirit of the research perfectly. It's all about precise control, about engineering things at the smallest possible scales to get a powerful, specific result. It's about building the perfect tool for the job, one atom at a time.
And that really leaves us with a final, pretty exciting thought. If we can design a custom nanoparticle to help clean the air, what else could we build? What other massive global challenges, from creating clean water to building better batteries, could we start to solve if we can just design the perfect material from the ground up?